18 new memberships, which is fantastic. Who here's new members? Yeah, hey, great to see you guys. So yeah, I'm Chris, who you'll see, you know, we get your emails and you're welcome back and all that jazz. Yeah. See you, Andrew. Everyone got a handout? Normally I do bullet points. I just was last night, still being midnight on about 10 p.m. So what I've done here, instead of bullet points I've gone through, I've just done the introduction and the summary of an article that I did on this exact subject. That's what I'm doing, which leads to an introduction about myself. The reason I'm doing this, I'm doing my master's degree in astronomy at Swinburne University in Melbourne. It's online. It's the only one in the world that does online with various people around the world. So I'm going to do a plug for Swinburne there. But also we have to do little research projects, and my research project was the role that liquid water has played on change on Mars. And we had to form an argument. So, and this is the article, or the summary of the article I just did for the handout. But if you want, it's in the journal about 2 or 3 months ago, but if you want a PDF just for your own interest to read it through the full article, don't be shy, just send me an email, either see Internet Extra or Membership Astronomy, and I'm happy just to flick you a copy just to read through it. It's an interesting topic. So that covers that. So it's about Swinburne. Yeah, it's an interesting subject and it's become very topical. The talks, these introduction to astronomy talks, which I try and avoid facts and figures too much. It's more the sort of the whole concept thing that we talk about. So we'll get underway. See if I can operate this. Yeah, and the other thing I should say, I know what I was going to say, is this around this whole topic too. The assignment that I had to do, all this is very controversial, and no one of course knows for sure. So my job was to go away, research all the literature that was there, and pull together it all together and see what sort of story was the most likely story that happened, and then form an argument backed up by all my research of what I thought went on. So that's what we're doing tonight, just going over my article really. So the starters, look, let's have some, Mars is very topical, it's a bit of an icebreaker, it wakes everyone up, relaxes me a little bit too. How can you have a Mars show without some Mars bars? Yes. Pump everyone sugar levels up, so we don't have this every time. It's a bit of a knowledge and I couldn't help myself. So some icebreaker quiz. Mars is very topical at the moment in a lot of regards. So who can tell me for a Mars bar the main sort of related to stargazing why Mars is quite topical? Everyone's talking about it.
Water. Found signs of water on Mars.
Yeah, that's coming down a bit. Yes, okay. So that's true. Yes, that was the July announcement. Yeah, absolutely from July. They have found, and this talk is of course all about the surface liquid water, but yes, of course, part of that story is looking for subsurface liquid water, and it's all been subsurface ice. But absolutely, in the South Pole regions, they found a lake about, they think. Once again, it's all suggestive, they don't know, but it's very suggestive of about 20 kilometres wide lake of liquid water. And of course, under those conditions, to be liquid, it would be very briny, very, very salty. That's probably not even how extreme a cold we're familiar would live in. But gosh, that's a very exciting find. So that's, yes, you've got the July announcement. One Mars bar. There's some double Mars bars and some singles, so it's pot luck which one you get. If you get the double, think you're lucky, because you've got twice as much chocolate. If you get a single one, just think that person's going to get fat. Just blood sugars or whatever it is. There's always positive spin to everything in life. Okay, how about for the stargazing? What's
the closest?
Yeah, absolutely. That's so. What's the technical name for that?
Opposition?
Yeah, opposition. Any particular, you can have your bar.
Yeah,
absolutely.
It's something like 60,000 years, but in fact, Grant says that it's not so much different. It's sort of more promotion.
Yeah.
That it's so close. It's just on such a small percentage closer than quite irregular.
So in the key here, because also it's what we call a perihelion opposition. So I thought I'd just run through that. So what happens with Mars? So Earth quite happily goes around the Sun once a year. Mars takes twice as long to work its way around the Sun. So it's about every 2 years that Mars is what they call, the technical term is at opposition, meaning we're here perfectly in alignment with the opposite one. The sun's in one direction and Mars is in the other. So that's what we call by opposition. Mars's orbit is also far more elliptical, meaning oval shaped than Earth's. So there's a period of time when it's a lot closer to the sun, called perihelion, and there are times when it's furthest in its orbit away from the sun, called aphelion. And it's because it just so happens that opposition is just by chance is happening exactly the same time as when it's at opposition. So it's perihelion and opposition all at the same time, and that's really brought it close. And you get an opposition every 2 years, but it just so happens coincidentally Mars is at perihelion, which is closest to the sun, which of course naturally brings it closer to the Earth. So that's why all the hoo-ha and fuss about it. How about the June announcement? What did they announce in June? They announced two things. NASA was a huge lead up to about 24 hours. NASA's about to announce something. Insight? Oh yes, they did announce it, but in particular, they announced two things.
It was possible organic material?
Absolutely. Complex, was that they'd already discovered some sort of basic organic compounds, but it was more complex organic compounds. Now that doesn't mean say there's life, it's a damn good start, other building blocks for life. And there you go, Brenton. Incoming chocolate. Last up. Oh, and of course the other thing, does anyone know what other thing they announced? Yeah, methane, fluctuating methane levels. Up till now, Curiosity had detected sort of fluctuating levels, had detected levels, very low levels of methane, but that hadn't been on the planet long enough to get a pattern. And it picked up, there's a definite pattern to the methane, goes up and down, up and down. So obviously there is some sort of active process that's producing methane. And the exciting thing about that, of course, is that sure, geological processes can cause methane, but so can biological, and biological is sort of the commonest way.
So is this methane in the atmosphere?
In the atmosphere.
Not on the surface?
Not on the, in the atmosphere. So Curiosity, so some process is going on. And of course, methane degrades itself very relatively quickly.
By what percentage does it fluctuate, or roughly?
I don't know the figures, to be honest. I just once again noted the concept, but that's great. But I don't retain those sort of figures.
So it's enough to...
Oh, the graph, yeah, so probably alluding to you, like say that's the graph there. The graph wasn't some little, it was, it was real, it was significant swings. It was in the summertime the levels of methane was going up.
Oh.
In wintertime they'd go down in the summertime. So most likely it's some sort of geological process. But that was quite neat how as soon as they detected a little bit of methane, we've actually detected a fluctuation. And the reason being that they've been on the planet now for 3 years. So that was the June announcement at the time. So that's icebreaker quiz number 1. Okay, quiz number 2. Only 2 quizzes. Who wrote, this is a song lyric, Mars ain't the kind of place to raise your kid, and as you're going to find out, it's as cold as hell. Bernie Taupin. Elton John wrote the music, but Bernie Taupin wrote the lyric. Greg. Does everyone know the song? Rocket Man. It's the song Rocket Man. Yeah, so as you'll find out, indeed, it's as cold as hell. So that was Bernie Taupin, like the lyrics for Elton John. That could be in the exam. Who wrote the song Life on Mars? Who was that? Was that you, Marion? Yeah. Who else did that? Oh, yeah. Actually, I noticed you're a new person and you've been quiet, you've sort of almost been there for most questions, so you can have one. Nice to be a member and chocolate bar. There you go. So you come back again. You ready? 1, 2, 3. Good on you. Okay, that's David Bowie. And one more. Who wrote the book and the movie The Martian? Andy Weir. Sorry, Andy Weir, yeah. No, Andy Weir, yeah. Bradbury wrote a lot of the science fiction stuff, and it was Andy Weir.
War of the Worlds.
Who wrote War of the Worlds? Yeah, that's not.
I actually know all the answers to your question, but I'm on diet, so I
There's two more, so we get to that's the end of the question. So just start, right, we're moving on. No more Mr. Nice Guy. Right, we're into some serious stuff now, guys. So when we started talking, it was nice to give you 3 main points I'm going to be driving home that I want you to take home. Is the current conditions on Mars are not suitable for liquid water, surface liquid water that is. There is very strong evidence that indeed liquid water has been present on Mars in the past, both geomorphic, geographic features, and spectroscopy from instruments on orbiters and rovers. Hey, my friend, would you like to come on in? Grab a seat. You sure? I'm going to take it anyway. I'm going to give it to you anyway. Someone's got to read my stuff.
geomorphic means what? I know it's
Land shapes, it's sort of geological land shapes.
Okay.
Yeah. Which we'll talk more about. So this is just giving you a rundown of where we're all heading for tonight, and your key message I really want to drive home. Mars clearly once did have suitable conditions. It did have a warmer, thicker atmosphere at one time, when probably 4.1 to 3.6 billion years ago, some time ago. And the bottom line is, Mars has undergone some huge changes, as you can clearly see that I'm insinuating. And what I want to talk about is how those changes occurred, why those changes occurred, and when did they occur. So, how I'm going to structure tonight's talk, just talk about the current, what's like the conditions that are currently on Mars. We'll talk about, and it's key to Mars, to talk about some of its background geological features and epochs or time frames. What is the evidence for liquid water? So we say there's liquid water. What is that evidence? And from there, what we can say about the early atmosphere, what's the climate like on Mars and the past, and its history, and then we'll sum up with a conclusion. So, its current conditions. So Mars, as you've seen in the previous slides, its orbit's further up from Earth. It takes about twice as long, about 2 Earth years to go around. It's about half the size of Earth. Its mass is 1/10. If you're walking on the surface of Mars, you're about 1/3 the gravity, the effect 30% of the gravity on Earth. It has an axial tilt of 25 degrees, which is comparable to Earth's 23.5, so very similar. And of course, it's the axial tilt that gives rise to your seasons. So there are very good, strong seasons on Mars, and of course, every 3 months on Earth, it will be every 6 months there's a season on Mars, because it takes 2 years to go around. The surface has got that very red hue to it, to the colour, and that's because of iron oxide in the soil, which is essentially rust. The atmosphere. The atmospheric pressure on Mars has a very, very thin atmosphere, very thin, such that the atmospheric pressure is less than 1% that we experienced on the season on Earth. The temperature on Mars, the average surface temperature is minus 60 degrees Celsius. Almost as cold as a student flat in Dunedin. Except as cold as hell. Great kids. So clearly, with those low atmospheric pressures and that low temperatures, liquid water is just not going to exist. It's either going to be in vapor form, with low atmospheric pressure, or because of the cold temperature, it's going to be in ice form. It's certainly not surface liquid water. So Mariner 9, 1971, that was the first spacecraft to orbit another planet, produced these grainy pictures of the surface of Mars. So already from the initial pictures, you could see quite clearly there's a lot of geomorphic features that highly suggested that some sort of surface liquid had flowed once. And the most likely candidate, of course, was always going to be water. So that immediately got everyone's interest and raised this whole topic. So, let's go through here. So we've clearly shown it does not support liquid water, so immediately that raised this big debate. What is the state of the past water? Has it been a liquid flowing through here? Has it actually been solid? Just ice like glaciers just moving, with bit of subsurface water and melting underneath the ice moving. So it's not taken for granted that it has been just pure liquid water. Has the water been above the surface flowing, either under a glacier, just on its own, just flowing in liquid form, or has it been below the ground in little channels? And then with time it's dried up and then the channels are caved in, much like you get those rills on the moon, where lava's been flowing afterwards. The lava's all gone and then it just caves in and it looks like water's flowed through there, but it's actually been under the surface. Where is all the water going now? If there was water there, what was the climate like to support it? And there's our big question: why, how, and when did the climate change? So just look and search for our winter. It was pretty obvious there was a lot that you can actually see that with your telescopes and home astrophotography, the polar caps. They were pretty clear. There's a lot of ice water frozen in the polar caps. Both polar caps have been estimated. The southern one recently, it's about the size of Texas, and radar have estimated to be about 3.7 kilometres deep of ice, the size of Texas. So if you melted all that, you could cover the entire surface of Mars with 11 metres of water, liquid water, should you melt it. And that's just one ice cap. And there's huge amounts on the northern ice cap as well. And you're probably going to say, which is the biggest? It depends. In the summer and the winter, the caps grow because there's carbon dioxide in there as well. In the winter time, the carbon dioxide condenses out of the atmosphere and forms a cap over the water. In spring, summertime, it sublimes back into carbon dioxide vapour in the atmosphere. Mars sent the Phoenix lander just out of the polar regions in 2008 to 68 degrees north, which is about here. You can certainly see that's well clear of the northern polar regions. And it dug under the surface. What did it find? Even that far down at 68 degrees north latitude, there was ice water underneath the surface, just under. You can see the size of the scraping. It's not very big, so it's pretty shallow underneath subsurface ice. This was last year. The study came out. I've done this from the high-rise telescope, high-rise camera rather, on the Mars orbiter, Constance orbiter, and I've done it in false colour. That is ice water they put in all subsurface ice water they put in false colour. You can see it's large deposits. That's actually taken about 39 degrees, so much even further down again. They also took photographs of some freshly exposed craters, and they looked at the craters side on. It was 100 metres thick of frozen subsurface ice going on. So clearly there's a lot. And the general consensus is, yeah, there's abundant water ice. Most of it's all at the surface of the poles, but there's a lot of subsurface ice that probably takes up about a third of the planet. So there's a considerable amount of water locked up on there, which really is in keeping with what we're seeing on the surface of the planet. Now, just before we go any further, it's important just to get a bit of a talk and an understanding of the surface geology and the timeframes on Mars, because that's all clues to the past. And the obvious thing you'll notice with this topography map is that the southern hemisphere is very high. They call it the highlands. It's very high altitude and it's covered in craters. And craters, if you analyse craters, particularly the size of craters, the density of craters, the numbers of craters, that gives you a guideline as to the age of the surface. And correlating crater counts with moon rocks on the surface of the moon, and then they in radiometric date the moon rocks, they've got a good correlation. So many craters of certain size with a certain density implies your surface is a certain age. Of course, the older a surface, the more craters you've got. So the southern hemisphere is what they call the highlands, heavily cratered, which means it's a long surface. Covering most of the northern hemisphere is all these flat lowlands, very few craters, which means it's a young surface. So that's known as Mars's crustal dichotomy, where half of the crust is really, really thick, half of it's really, really thin. All sorts of theories. It's probably from a large collision that occurred early on in Mars's formation, and then lava's filled up here. The other thing to note is you've got a thing called the fastest bulge. It's a huge big volcanic plateau that takes up 25%, a quarter of the surface of the planet. And there's 3 volcanoes all in a row there. So that's a huge big volcanic plateau, the fastest rise. Just over here you've got the largest volcano in the solar system, Olympus Mons, which stands at about 22 to 24 kilometres high. So just imagine that, 22 kilometres high. What's Everest, about 5 or something, isn't it?
8, I think.
Hey, sorry?
7 or 8.
8, yeah. So that this is 3 times the height. So you can imagine sort of rocks and stuff spewing out of there, going right high up into the atmosphere, to the thin atmosphere. You might think, how can it get so high? Actually, what's one of the reasons why you get this huge high volcano? Did you want one? Well, yeah, I've got to give them away anyway. Let's just toss one in this direction. Yeah, well, there you go, guys. Oh, sorry. Okay, yeah, let's grab it. Let's say before one come up. But the other thing is Mars is a one-plate planet. Yeah.
It's because it doesn't move, it just
You little beauty.
flows and flows and flows forever.
Yes, you little beauty. Absolutely. Mars is a one-plate planet. Instead of Earth with relatively thin plates that all slide and move and groove around and keep moving and are relatively thin, Mars has got one thick crust.
Sure. How would we know that?
Yes, that's a whole probably talk on its own. But okay, I'm not a geologist, but they do that through sound, the same as they know to Earth's crust. Insight is going up there to do some further research, but they're pretty certain it's a thick crust. There's a lot of it is the geology of it. They look at it and they can't see any tectonic things, but also they know from you can tell the density of the planet, by the way it moves, it's all of that information.
Another question now, all of that blue on the top,
Yeah.
that's not water.
No, we're going to talk about that sugar water. Yes.
Water's close to the pole.
Yeah, correct. It's not frozen water.
That's
Now,
just the height, is that the altitude?
it's just, it's very low. They're lowlands, the northern lowlands. They take up about 1/3 of the planet, and that is the site of the Mars ocean hypothesis that we're going to be talking about later on. So it's a one-plate planet. It's got one big thick crust, which immediately, one thick crust, it can support a big solid structure without cracking. But also, as Lara said, what happens on Earth is you get some magma coming up in one spot, a hot spot, but you've got a plate moving over it. So it bursts up here, but the plate's moving, so it bursts up here, and each part of the crust has been cut off from its magma supply. And what do you get? Hawaiian chain of islands, classic example. You've got a plate moving over a hot spot of magma, so you get a series of islands. That plate just sits there still, it's not moving. So it just keeps piling up, piling up, piling up. It's got low gravity to support higher things, and it's got a big thick crust to handle and hold that weight up without collapsing.
Wouldn't the 3 volcanoes in a row there kind of indicate a similar thing to Hawaii there?
The 3 separate hotspots. Yeah, there's no tectonic plates, but I know you live. Yeah, you're quite right. Yeah, that's a good question to ask. All 3 in a row. They're just 3 separate hotspots. Yeah. You've got another volcanic region over here, the Elysian region as well. So there's a bit of volcanic activity that has been going on in Mars. There is some research suggesting that within the last few hundred or thousand years there's been a bit of activity from rocks. And then you've got there's a big crustal fault line through here. Probably it's from a fracture, and that's called the Valles Marineris, because the Marineris spacecraft first identified it. Now, check out this, guys. Tony, I'm going to tell you. Check out this. I was only joking, Tony.
Sorry, I
We
didn't
didn't
notice.
hear.
Oh, no, because you were talking to Marilyn. I'm only having you on.
Oh, that's
I'm only having you on. I'm just joking. It was fun. So this here, this Valles Marineris, 4,000 kilometres long. Okay, that's almost the width of the United States. It's 200 kilometres wide, and it's about 7 kilometres deep. So that just puts the Grand Canyon to shame. So it's huge. It's probably some sort of crustal fault. We just, this big forest rise has risen and it's split the crust, and one lot's dipped down and one lot's come up.
The dark blue spot on the lower right, so that means, the dark means it's very deep.
It's very deep. That's called the Hellas Basin. Huge, massive deep impact crater. Correct. Yep. So with that, there's mentioning sort of analysing craters. They're able to get an idea of the time frames. So they then try and match that up with geological features that are going on. And we're going to talk about all these outflow channels, valley networks, and so on. You then relate those to the time frames to what's probably what sort of geological activity was going on, volcanism, the heavy bombardment phase. That was when the whole inner solar system was bombarded with multiple numbers of asteroids because of the outer planets were moving around. And they put these into time frames, and the reason I put this up here, you'll see the more you read about Mars, the more you'll see here, they call it the Noachial region, which is, these time frames are not definite, they vary a lot from paper to paper, book to book. That's the general consensus, probably 4.1 to 3.7 gigayears, that's billion years, that these sort of processes were going on to explain these features here, and that's called the Noachial region, epoch or time frame, Hesperian time frame, when you'll see that, as you'll see shortly, Mars was very wet here, it was getting a lot drier and colder here. That was 3.7, 3.0, sometimes you read that down to 2.8 gigayears. And then within the last 3 billion to 2.8 billion years, it's been known as the Amazonian period, where it was very cold, very dry. There was some volcanic activity where you probably experienced this northern plain getting laid out. So I put that in here because the more you read and hear about Mars, the more all this sort of jargon becomes relevant. So let's move on. What is the evidence of past liquid water? You break it into two features here. One is the geomorphic, that is geological sort of land shapes, if you will. And we're going to talk about these 4 items here. And then spectroscopic, that's sort of spectrological analysis, analysing the light that's reflected off minerals, and from there you can look at the sort of fingerprints, if you will, and you can tell what sort of minerals and types of rocks there are. That is, they've got a lot of information from the orbiters. Tonight I've concentrated on 3, Gussif Crater, which is the landing site of the Spirit rover, the Meridian Planum, which is the site of the Opportunity rover, and Gale Crater, where Curiosity is still busy working away. And I've got interesting little bit here, Martian meteorites. So geomorphic features, so there's main things here, valley networks, outflow channels, lakes and deltas, and the Mars ocean hypothesis. So let's start with valley networks. See here, these are sort of systems of branching individual channels. And each channel here, and these are very clear on Mars, I've seen these from early on, they're only, sort of say hundreds of kilometres long, just a few kilometres wide. They see predominantly, they're in those southern highlands with the Noachian surface. Clearly, sort of, you're talking probably 3.7 out to about 4.1 billion years ago. So early on in Mars, these were appearing on the surface, and clearly that looks very suspicious for liquid water. When you go into the Hesperian surfaces, meaning younger surfaces, probably about 3 billion to 3.7 billion years old, called Hesperian surfaces, you're starting to see them to a lesser degree, and then over the Amazonian terrain, the younger ones, that you start seeing less and less often, which means whatever was causing these processes stopped about 2.8 billion years ago. So that was one of the first oldest features on Mars, is these little systems of relatively narrow, relatively short sort of networks of valleys, individual valleys. So you might say, well, what caused these? And there's 4 different possibilities, scenarios, and every single one of these has a very solid argument backing it up. Was it a warm and wet environment that caused that? In other words, rainfall coming down, it was wet, it was raining, and you had surface runoff and erosion. That could have caused this. Was the planet warm, but was it actually dry In other words, it was geothermal activity bringing water up from underneath the ground, and that was flowing. Was the planet cold and wet? In other words, it was wet, it had precipitation, which means rainfall or snow, but it was snow, it was cold and wet. So it was snowfall and coming down, and glaciers forming and drifting down, eroding the surface. Or was it cold and dry? In fact, there was just ice sheets and ice caps everywhere, and it was just water melting underneath, what we call meltwater, flowing underneath the ice sheets. There's arguments for every four of those. You might think, really, how about this? There's areas in Arctic Canada that have features just like this, and it produces these exact things. So think, which one is it? Could be all four or what? But with time, they took better and better pictures. And the MRO orbiter has taken some really high definition, the high-rise camera takes some really high definition pictures in recent years. And you'll see the branch, look at the detail coming out here. The branching is really high order, just keeps going out and out and out. There's a lot of, you can't see it, but there's terracing in here, there's bits of exposed bedrock, and that very, very much more favours rainfall, with surface runoff and some erosion going off causing the exposed bedrock. So that there is one argument saying that it was warm and wet once on Mars in those early times. Once again, that's telling you it's more like in the southern highlands and the Nokian sort of area, which was what, about 3.7 to 4.1 billion years ago. So you're getting the gist of it already. You're looking at features, looking at what surfaces they're on, how old the surfaces, and you're getting a time frame of what sort of processes were going on. Then you see these big things called outflow channels, and these are completely different beasts. Much, much longer. You're talking of thousands of kilometres long and hundreds of kilometres wide. Those valley networks, the individual channels, were probably sort of 100, 200 kilometres long, only little bit narrow little things, sort of 10 or 20 kilometres wide. These things are big. They often originate, this is just part of one, and you can see how large amounts of water has obviously flowed quickly, created little stream islands here, and some of them is flooded out here in the lowlands. This is only half it, the rest of it's over here, and they've located at the beginning of most of these large craters or depressions, what they call chaotic sort of surface, where it's been sunk down a little bit, and it's just there's no pattern to it. Something sort of big and chaotic, some event has happened. And I think the general theory is that as Mars did get colder, more and more water went subsurface with time. It built up more and more pressure because ice expands. Then you get this huge big reservoirs of water. Suddenly you get an outburst because it wasn't all cooling down uniformly. Temperature would go up and down as the trend goes down. You get a warm patch. Suddenly the pressure was too much. You get a huge outburst of liquid surface causing flooding, a big gush of huge amounts of water pouring on down. And these outflow channels are mainly seen in the surfaces that relate to the late Hesperian period, which is sort of talking 3 to 3.5 billion years out there. So it's all in keeping with a lot of water above the surface, rain, as time was going on, it was getting colder, water was going down underneath, but still bursting up to get a little warm patch and causing these big outflow channels. Lakes and deltas, absolutely, and this is just a false colour thing item here with sort of laboratory type of thing. That's showing if you get a big crater or a lake here, and you get water can flow into it, and you get little deltas forming in here, and you can see this here is Elderswald crater, and you can see this is just near the start of it here. Look, you can see all this delta formation where obviously fluid has flowed into a large crater, and it makes sense. You've got these huge big craters that are obviously formed early on. You're going to have rain, these things are going to be prime things for lakes. So obviously that's where they wanted to send the landers to see if standing water, never mind flowing water, was there standing water. So with lakes you get flowing water through, into, breaking on through the rims of craters. You're going to naturally going to look for if there's thick sediments in there, and indeed that's what they did see. So let's move on. No, okay, I know what I've done there. I've then moved on, and we're going to talk about that with Gusset crater. So you can see valleys cutting into it, these huge big deltas, flat floors. Most of the craters do have flat floors, the big craters. So moving on, so that's lakes and deltas. Hold that thought, because we're going to look at Gusset crater where it's spirit landed. So the Mars ocean hypothesis is growing evidence. There's a little bit of doubt and argument about it all, a bit of debate, but there's strong evidence that northern lowlands that take up about a third of the planet was actually an entire ocean. If you're going to have this rainfall, you've got to have a large reservoir of water to keep a hydrological sort of cycle of water being evaporated, carried and dumped elsewhere on the planet. And this would fit in with that quite nicely. It's on the lowlands, it's in the young surfaces as well, so that ties in nicely. One of the main arguments against it is the boundary between the lowlands and the highlands is anywhere between 6 and 3 kilometres, so that's how much it can vary. And it's quite a complex boundary. The argument being, how can you have such a complex boundary and ocean shoreline? Some recent research with computer models has shown that as the farthest rise, the big volcanic plateau forms, it would have thrown and wobbled the planet a little bit, and that would have, they said that matches perfectly how the ocean shoreline would have changed. Yep, further support with there. There's all leading here, you get these big channels and networks all heading towards the ocean, and along the proposed shorelines, there's a lot of delta deposits where clearly water's flowed into standing water and you form these big deltas. So there's signs of that. The other thing is too, is when they measure the water, the ice water obviously, on Mars, there's two types of water. There's the H2O, the two hydrogen atoms combining with oxygen. And we know that hydrogen is one proton and one electron. But there's an isotope of hydrogen where you get a neutron put in there as well, and they call it deuterium. And it's just an isotope of hydrogen, still got the proton and electron, so it's hydrogen, but it's just got a neutron in there. So it's a little bit chemically heavier than normal hydrogen, and for that reason, when you get deuterium and hydrogen and oxygen, they call it heavy water. You may have heard of that expression before. And you get a certain ratio to expect in planets of the heavy water ratio to the normal H2O, which would be a certain ratio that you get, for example, on Earth. And when they did measurements of how much is in the ice of both these, of the isotope, the heavy water versus the standard water, there was proportionately too much heavy water. So clearly Mars has lost some standard H2O somewhere in the history. It has been lost from the planet. And of course that fits in, if you're going to get evaporation of water, what's going to evaporate first and drift upwards? The lighter one, the H2O, and the deuterium heavy water is going to stay behind preferentially. And indeed, that all fits in with the picture as well. So now moving on to spectroscopy, it's studying the light that reflect of rocks and minerals. Each rock and each mineral type gives off a standard type of spectroscopy pattern. And we're going to look at these. I thought I'd pick on the 3 landing of the rovers sites and talk about the Martian meteorites. And also notice along here that all these guys, all the rovers and landers have all been on the boundary between the north and the southern. And the reason they did that, the north is a little bit boring, a lot more of the exciting stuff happening on the southern side, but you've got a thin atmosphere to come down, so you need a lot of atmosphere to slow a spacecraft down. So it's going to be a lot easier to land in a setting that's another 6 kilometres lower. It gives you more atmosphere space to come down and land properly, and you're landing on a slightly flatter surface, which is a bit more safe. So for geological reasons, the geologists were trying to say, no, land over here, guys. The engineers were saying, no, land over here, guys. And they found some compromises where to land this. So this is Gussive Crater, where Spirit landed, and you can see here what I was going on, what I was practically on about before. You can see there's a big crater that's about 166 kilometres wide. You see it's got a nice flat floor, and that's probably most likely sedimentary sort of minerals and rocks and material there. That was good. You can see here where large channels come through. It's broken through the rim of the crater, and you can see it looks like stuff has been deposited here. So I thought, hey, that's a good place to land. And indeed, that's where the Spirit landed. And when they did the analysis, they found a lot of interesting minerals, sulfates, geophyte, carbonates, and those minerals only form in the presence of water. They don't form in dry conditions. And they found some pretty good evidence of those. Olivine is another mineral that you usually find in dry environments because water decomposes it. They found a lack of olivine, which you should have seen there, but it was lacking. Instead, it was all full of these guys up here. So that immediately suggests the presence of water has been there. There was a period where Spirit got stuck and one of its legs stopped working and it jammed, so they started dragging it backwards, and that unearthed some of these minerals. Then it further got stuck in a little sand trap. What do you do when you get stuck in a sand trap? Just 3 wheels and one stuck. You just plant it. They did some wheelies to try and get out of there. And doing the process of doing the wheelies, they actually uncovered some silicous-rich soil, which usually confers some geothermal hot spring environment going on, which means there was some liquid water going on, probably subsurface with some heat coming out underneath it, causing some springs. So in aging the surface, this was probably in the sort of late Noachian age, so you're talking about 3.7 billion years ago that this sort of process was going on in this crater. The Meridian Plani, where it's, remember, Opportunity and Spirit for the twins, they both landed at the same time in January 04, if I recall. And you see that Meridian Plani is a lovely big plain. You think, why are they there? It did have some interesting craters, which were within reach of Opportunity, but also one of the Mars orbiter had detected a lot of hematite. It's a mineral that's closely linked with water. And there was a lot from the orbiters that detect a lot of hematite sitting around in this region. But let's go in there. I put this picture because that's quite a neat picture. It's the back shell and the parachute left over from Opportunity. That's the back chute's the thing that protects it. Comes down, ejects those, and then goes and lands and lets those fly off in another direction. And Opportunity managed to get a picture across the plane of its own hardware. So that's the reason for that picture. It's just quite cool. So let's have a look at some of the features that were discovered by Opportunity. Spherical blueberries, that's hematite, that typically forms in hot water and standing water, so not cold water, not flowing water, water that's lying around in hot water. And there's a lot, they call them nicknames called blueberries. There's loads of these to be seen. And also veins of gypsum. They've looked at some sedimentary rock. Once again, sedimentary rock is usually deposited by water. And gypsum is a mineral that's formed in water. It's a sulfate mineral. And you can see little veins. So that was probably water underground flowing through some sedimentary rock, and then it's all solidified. Thugs. And the little grooves that you see in rocks, and that's where sulfate, once again, sulfate is a mineral that forms in water, and you can see that that's obviously formed inside rocks. Water's probably gone through and dissolved it and left these little gaps here, called bugs. That's probably the right bugs. Just looking at more geomorphic things, look at these rocks have been laminated, cross-bedding and so on. That's usually seen on Earth where you get gently flowing water. So those images are quite plentiful from Opportunity. So moving ahead to the Curiosity lander, and that landed at Gale Crater. Gale Crater is about 154 kilometres across, so it's a decent sized crater. In the middle there's a 5.5 kilometre high mountain called Mount Sharp. And that is thought to be just multiple layers of sedimentary rock that's been built up over the last few billion years. So not only can you get in there and analyse that rock, but as you move up the mountain, you're going back through geological history. So that was just absolutely, brilliant place to land. They landed here, and they put a Bradbury landing after the science fiction writer that someone mentioned over there on Mars. They found a huge big delta sitting over here. Slowly it's been working its way across, and now Curiosity is working its way up Mount Sharp. And what has it found here? As I mentioned, a lot of delta-related deposits, the type of minerals that get deposited in deltas you see on Earth. A lot of sedimentary rock that is related to water, not necessarily wind, such as mudstones and sulfates. Pebbles and gravel, that's formed from flowing water. And that's an artist's impression, most likely when they built the picture up, probably what Gale Crater looked like. this huge big mountain of sort of time stamps of different geological times. You can see a nice channel running through, breaking through the rim of the crater, filling it up. Meteors from Mars, really? Absolutely. We already talked about how you've got huge volcanoes high up in the atmosphere at Mars. It's got a very thin atmosphere, so there's not a lot of atmospheric resistance. It's got a low gravity, so it's very easy for a volcanic rock to come up out of Olympus Mons and come heading our way. You also get a large impact, say from an asteroid, just ploughing into Mars, flies rock up really high. That rock's got easy enough to get the escape velocity to leave Mars. And indeed, there are meteorites that are found on Earth that come from Mars. You might say, how do they know from Mars? There's little bubbles of gas inside them, and they match the oxygen, or rather the gas composition rather, with the gas composition that they know on Mars, in particular from the Viking landers in the 70s, pretty early on analysed the constitution of the Martian atmosphere. And the little bubbles of gas there fitted there perfectly, so it was pretty clear these guys came from Mars. And when they looked at some of the minerals identified, so instead of relying on a rover, suddenly you're actually looking at it in the laboratory on Earth. And yet there's minerals in there that have formed in liquid water. So we've got pretty good evidence on land features and minerals. So how do you explain all this? What would have the early atmosphere have been like? Was the planet cold and dry when it was in its youth, when it was young? Or was it warm and wet, young planet? And if so, all of this, how did it lose its atmosphere in the water? What happened to it all? If we talk the first one, a cold and dry planet, it's easy to imagine a cold and dry early Mars, very easy. It's 50% further out from the sun than the Earth, so it's going to be a lot colder. So immediately that tells you, it's only got 43% of the amount of sunshine it's hitting it. From just models of stellar evolution, type, we're a G2 stellar spectral class sun, and we know that about 3 or 4 billion years ago, the sun was 25% luminous than it was. So at the time when all this was happening, these features, the sun, it was 40% less brighter than it would have been on Earth, and it would have been 25% luminous than it is now. Periods of high obliquity. Obliquity refers to the axial tilt of your planet, which gives you seasons. If you get extreme high obliquity or high tilt, that immediately tends to push all the ice, the coldness from the polar areas, brings it forward towards the equatorial regions, shifts ice around and brings it more to the centre of the planet. There is good computer model evidence that Mars has experienced it very wobbly, it's unstable. We take for granted our axis is stable. That 23.5, that's because we owe that to our moon. The gravitational effect of the moon just holds that reasonably stable. Mars does not have a moon like we do, so it's very unstable. That obliquity, it has changed. There's evidence that suggests it's changed from its 25 degrees up to 40, possibly 60 degrees tilt. So that could have easily have driven all the ice cold down to the equatorial regions, all supporting the concept of a cold and dry young planet. So you would have had standing water and flowing water both under ice sheets and glaciers, and that would have accounted for the erosion. Yep, that's all good. There's a problem with that. It does not explain those real high-definition complex branching valley networks that favour process of precipitation, rain or snow, coming down in a wet environment versus a dry environment, causing erosion and all that high degree of branching. So there's a problem with that idea, as attractive as it might seem initially. So was the planet then warm and wet with rain and or snow? There's a problem with that, of course, is for rainfall and liquid water on the surface, you need a much warmer and thicker atmosphere than you've got now, or there would have been there. So what sort of solutions? You've got various mechanisms, three main mechanisms how that would have been achieved. Volcanoes in those early days, after the formation in the first 500 million years, you saw there's a lot of volcanoes there. Mars has experienced a lot of volcanic activity. They would have been spewing out carbon dioxide and water vapour. All those are have a strong greenhouse effect. That would have been quite happily raised the pressure and the temperature of Mars. Also at that time, you get up to a certain point, methane is often trapped, you know that from Earth, under subglacial regions, you get methane gas trapped underneath there, can't get out. You start getting a little bit of warming, you reach a threshold, that starts getting released, and methane is a very potent greenhouse effect. That starts rising even more. In those early days, those time periods we're looking at, you saw those heavily cratered surfaces, which they call the heavy bombardment period. That was when the outer planets were migrating and shuffling around. There was a huge number of asteroid and comet impacts on all the inner solar system. When you get an impact at high velocity, you release huge amounts of energy. That also, that heat of impact, that generates enough energy to further raise the temperature. And that is well supported by computer models. So there's got three very strong mechanisms there for raising the atmospheric pressure and temperature. So, but you've still got a problem. What happened to all the water in the atmosphere then? What's happened to it if there was more of all this present in the past? The atmospheric pressure of CO, of carbon dioxide and water vapour clearly must have declined. So how, when and why? That's the root cause of everything. There's three possible solutions. CO2 quite happily gets absorbed into rock as carbonates to create a carbon cycle on Earth. But when the orbiter analyses all the rocks, there's no real evidence of much carbonates on Mars to really talk about, so it can't have been that. It could have condensed into the poles as CO2 ice. And there is CO2 ice at the poles, but the polar ice is pretty much 99% water ice. And CO2, when it comes to spring and the summertime, it sublimes or evaporates back into the atmosphere anyway, so unlikely to be that. So that leaves you, the other mechanism was probably lost to atmospheric gases that escaped out to space, and indeed NASA's Maven satellite that's researching just purely on this whole, the conditions of the upper atmosphere of Mars, is certainly consistent with that process. And so how does that occur? We take for granted we've got a nice big thick liquid molten iron core inside Earth, and as the Earth rotates, the iron turns round and round. You get something, iron conducts electricity, you get moving, conducting electricity, you get a magnetic field, and that gives us our magnetic field that goes right around the Earth. And this month's journal, I just put an article in there about global magnetospheres of planets, particularly Earth and Mars, that you can have a read there of how that happens. So Mars didn't have, stars didn't have a big molten core as Earth. Why? We collided with the theatre, we formed the moon. We pinched a lot of liquid nitrogen off that other protoplanet that collided with us to help form the moon. But also, Mars, being a lot smaller than Earth, has a larger surface area to volume ratio, which means it cooled a lot quicker, which means that relatively small molten core cooled a lot quicker and solidified. You lose your magnetic, your global magnetic atmosphere effect. So it's lost its global magnetosphere, which magnetic field lines going around the planet, which means suddenly the planet's, the upper atmosphere is left exposed to all these solar wind charged particles heading past at about 500 kilometres a second. Zip past, and they just, the charged particles, they just rip into the atmosphere. They disassociate carbon and oxygen. They disassociate hydrogen and oxygen. So they split them up. So suddenly you've got light hydrogen instead of a water molecule. You've got an oxygen and a hydrogen that's light, it can easily fly off into space. You get a carbon dioxide, suddenly that's split up to carbon, and oxygen, that flies off. So it slowly erodes the atmosphere. Currently, Martin has calculated, right, this current date would have been worse then, of course, because those things taper off because you've got less atmosphere. So you would have a heavier, thicker atmosphere, you would have lost at a higher rate. But even today, 2 kilograms of atmosphere per second has been lost from Mars out to space already. So you imagine that process. When did it start happening? They suggest, computer models suggest about 4.1 billion years ago that it probably the molten core solidified. So that process just would have slowed, it wouldn't have suddenly happened, but it would have slowly started happening and gathering momentum as the magnetosphere started dying down. And then it would have got up to a cracking pace, and then of course the atmosphere's got thinner, so the rate of loss is slow. But it's still 2 kilograms per second. So, let me start summing up. Main points, take home, is there's a lot of geomorphics with land features of past water and sub-liquid water, such as your valley networks, your big outflow channels, your lakes, your deltas. Good evidence support a huge big ocean, taking up a third of the planet, to allow for a hydrological cycle with evaporation and then rainfall elsewhere on the planet. The valley networks that support rainfall, probably in the southern highlands, probably in the Auckland epoch, which suggests about sort of 3.7 to 4.1 billion years ago. The outflow channel, clearly things would get going underground, but that pressure would build up and get released. They all flood towards the Northern Ocean. So there's a lot of surface sort of features there that suggest liquid water and rainfall. Spectroscopy shows a lot of sort of pebbles and rock lamination minerals, all consistent with wet conditions in the Nokian and the Hesperian epochs, which takes you from 4.1 down to about 3 billion years, starting to get colder and drier. Volcanism and large impacts, plenty of evidence of that on the planet, quite capable of producing a thick and warm atmosphere to have provided that liquid water on the surface and that rainfall. It can all be explained by Mars cooling, by the loss of the global magnetosphere, which then leaves the atmosphere wide open to be stripped away of its CO2 and O2. So those are your main points that you've got from here, evidence. So let's pull this together. What is your most likely sequence of events? It probably kicked off with a lot of extensive volcanic activity, as all planets were in their early stages. They were just spewing water and CO2. That raised the pressure and the temperature up to the first 500 million years. And from then on, large impacts created more heat, and you've probably got some methane release. That would have quite happily created that early, thick, warm, rich atmosphere. A lot of evidence for the rainfall and the snow and the flowing ice has evidence from the valley networks and the water flowing from the highlands down towards the lakes probably occurred at about 3.8 to 2.8 gigayear, in other words, through the Hesperian epoch down into the early Amazonian epoch. By then it was getting colder and drier and that was thinner. You started losing those features. Then the loss of magnetosphere amongst all while that was going on, but the atmosphere started going down, and slowly over that period of time the liquid water was slowly turning to ice and glacier formation with underground water. It would be underground liquid water, which would be protected. And then slowly, as you get little pressure building up, the outflow channels appear from the crater counts looking at the surfaces, probably 3.3 to 3 gigayears. So all the sort of exciting stuff was happening probably at 4.1 down to about 3.7 billion years ago, and then that bottom 700 million years to about 3 giga, it was slowly getting colder, building up inside with occasional outbursts. And then really, just from about 2.8 billion years onwards, the atmospheric pressure had just reached a critical length, a critical period where there was low pressure, low temperature, where liquid water on the surface really had given up. And it was pretty much surface water all evaporated, lost to space, with what was left below, which is a high proportion of the heavy water, which was less likely to be evaporated up, remained as groundwater freezing into subsurface ice and in the poles. And that's what they're analysing now and finding that higher proportion of that heavy water, which is further evidence to say, yeah, most of the water has been evaporated. That's a likely sequence. Concluding, so 4.1 to 3.6 billion years ago, Mars probably was warm and wet with surface liquid water. Then from about 3.6 to about 2.4 billion years ago, mixed regional conditions getting colder and drier, turning to snow, ice and glaciers. And from about 2.8 billion years onwards, it has been cold and dry and remains that way. I'm going to leave you with an interesting thought. Food for thought. 3.7 gigayears is sort of the estimated time looking at fossils and so on, where they suspect the evidence point was life probably arose on Earth about 3.7 billion years ago. 3.7 billion years ago, conditions on Mars were far more suitable for life. We also have seen how Mars can quite happily travel from Mars to Earth. Awful argumentations. But more important than that is enjoy your Mars bars, and thank you very much. Drive home safely. Thank you. Any questions apart from Mars bars?
Are there any glacial valleys, moraines?
Well, there is arguments that some of those valley networks could have been other glaciers, but as the more higher resolutions pictures came out, they were too sort of complex and too branched, high-ordered branching to really explain that. You'd expect some more broader branching. But presumably there's probably some features, that's why there's some guys still arguing for it. And there's some of those features are very similar to some of the Arctic Canadian glacier features. But yeah, really the key point here was those high-order branching patterns that as the resolution of the pictures got better and better. Yeah, John?
So what if people are aware of the fascinating history, of the Italian astronomers who thought there were canali on Mars, which actually translated as channels.
Yes.
There was a thought that man made in the 19th century, I think, with clearly high resolution telescopes. And I feel they must have been picking up some of these features.
Yeah, well, it's interesting you say that because Lowell, for the Lowell Observatory phone, he was the late 1800s, early 1900s, wasn't he? And he was a real advocate for these. But it so happens that it really wasn't optical illusions. There are no corresponding channels. Because you think, oh, clearly they were looking at that and that. But no, it's turned out that they were just optical illusions. Who knows? It was dust patterns, but they were optical illusions. There's nothing we know now about the structure of Mars. But yeah, they genuinely believed there were Martians up there with had engineered canals, probably taking water from the poles to the equatorial regions. And so you could see why all it takes is War of the Worlds from H.G. Wells. Oh my gosh, they're on their way. So yeah, absolutely.
But it's also part of their knowledge and technology at the time is what their brains interpreted.
Bias. It's a bias. I heard what Brian Cox, someone said, look, I've seen UFOs. Let's not talk about that. I know about UFOs. We want to talk about the aliens. Brian Cox, woo, back up the bus. When you say you've seen a UFO and you know all about aliens, what did you see? Oh, something shimmering in the sky. And he made this beautiful point. He says, and then he stopped himself. He says, pardon me, our human beings, our eyes and our visual processing centers and the occipital areas of our brain is very biased. What we see and what we process, what we think we're seeing. We see a silver thing and all we really did was see a flash of light and our brains are itchy. Oh, I think I saw something sharp, something to shake thing there. So he said, so let's get that right. Now, what was the original question? He said, so in what Andrew's saying, they would have been very biased. They saw these lines. Oh, they're channels, channeling water. So, but yeah, it's good, interesting. Yeah. Any other?
Meteors from Mars.
Yes.
What ones who want to meteors from Mars? I mean, like from meteors came from Earth, so like planets and then like any other.
Oh, I see. Yes, because there's a whole theory around panspermia. One of the theories how life got started on Earth. It could have come from an asteroid or a meteorite or a comet hitting Earth as a meteorite, hitting Earth, and it had microscopic life on it, which then took hold on Earth. And that's a very reasonable theory that's been thrown around, panspermia. And of course, if it comes from meteorites, you would think of asteroids and comets. But as we've seen, asteroids, meteorites can come from Mars, like planets. So, and it just so happens that 3.7 billion years ago, when they think life arose on Earth, life was at that moment in time, life was far more likely to have formed on Mars. Conditions were probably far better than they were on Earth.
So the only one with the is that from like interpreting on Mars, like what was actually.
I think we're talking microscopic sort of, microscopic sort of single cell organisms that then just came, that were just in the rocks, nothing too fancy, just single cellular life that were in the rocks, meteorite an asteroid hits Mars, flies it up into the air, escapes very easy, low atmospheric pressure and resistance, low gravity, easy flies up, heads around in the solar system for a few million years, and eventually smacks into Earth, and the singular cell life just takes hold. And so, oh, this is a nice place to settle in. Yeah. So that's just the food for thought. Who knows? Yeah. 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 Are we all good? Anything else? All right, guys. Safe travels. And next month we're doing a talk on the solar, a modern